Alright, let's talk about something called a priority queue. Imagine it as a special type of line where each person has a priority number. The cool thing is that the person with the highest priority gets served first. But if two people has the same priority, then they are served based on who arrived first in the line. Now, how do we decide these priorities? Well, usually we use the value of the thing itself. For instance, if we are dealing with numbers, the bigger the number, the higher the priority. But sometimes we might flip that around and say the smaller number has a higher priority based on our application. And the great thing is, you can set these priorities based on whatever your need for your task. It's like giving importance to different tasks on your to-do list. Now, let's talk about the difference between a normal queue and a priority queue. So, in a regular queue, the rule is first come, first served. Imagine standing in a line at a food truck. The first person is in line gets their food first, then the next, and so on. But in a priority queue, it's a bit different. Here's the important thing is the priority attached to each of the items. The one with the highest priority gets served before the others. It's like a special line for VIPs. So even if someone arrived later, if they have higher priority than others, they got served first. Alright, let's talk about how we can actually put this priority queues concept into actions. You can implement a priority queue using different tools like an array, a linked list, a heap data structure, or even a binary search tree. But among these options, the heap data structure really shines when it comes to efficiency. So, in this tutorial, we will focus on using the heap data structure to build our priority queue. Specifically, we will use something called a max heap. If you are curious about how max heap works, you can learn more about them by checking out materials on max heap and min heap. Now, if we compare different implementations of the priority queue, you will see some differences in how they handle operations like peeking, checking the top element, inserting and deleting. For the linked list, the peek operation has a time complexity of big O of 1 as it directly accesses the head of the list. The insert operation has a time complexity of big O of n as it may require traversing the entire list to reach the insertion point. The delete operation has a complexity of big O of 1 as it removes a node given in reference. For the binary heap, the peek operation has a time complexity of big O of 1 as it retrieves the root element directly. The insert operation has a time complexity of big O of log n as it involves restarting the heap property by traversing the height of the tree. The delete operation also has a time complexity of big O of log n as it requires adjusting the heap structure to maintain the heap property. For binary search tree, the peek operation has a time complexity of big O of 1 as it directly accesses the root node. Both the insert and delete operations have an average time complexity of big O of 1 as they traverse the height of the tree. However, in the worst case, they may have a time complexity of big O of n if the tree is unbalanced. So, when we consider all these factors, using a binary heap for our priority queue seems like a great choice due to its balance between efficiency and ease of implementation. Alright, let's dive into the essential actions we can perform with a priority queue. So, a priority queue involves three main options: inserting a new element, removing elements, and peeking at elements. Now, before we delve deeper into how a priority queue works, it recommends taking a look at the heap data structure. It will give you a solid foundation on binary heaps, which we use to build and understand priority queues in this discussion. This knowledge will really help you grasp the concepts better. Let's now learn how to add an element to a priority queue, particularly a max heap. This process involves a couple of simple steps. First, we insert the new element at the end of the heap. Then, we perform a step known as heapify. This essentially ensures that the heap property is maintained, meaning the parent node should be large for max heap or smaller for min heap than its child nodes. Here is the algorithm for inserting an element to a priority queue, which is a max heap. If there's no node, create a new node. If there are already nodes, insert the new node at the end, which is the last position from left to right. Perform heapify on the array to rearrange the elements and maintain the heap structure. Remember, for a min heap, we adjust the algorithm slightly so that the parent node is always smaller than the new node. This ensures the proper order in the heap. Now, let's delve into the process of removing an element from the priority queue, particularly a max heap. This involves a series of steps to ensure that the heap properties are maintained. Here is how you delete an element from a priority queue, which means a max heap. First, you identify the elements you want to delete. Then, you swap this element with the last element in the heap. So, after the swap, you remove the last element, effectively extracting the element you intended to delete. So finally, you perform heapify to reorganize the heap and maintain the proper order. So here is the algorithm to delete an element from a priority queue. If the node to be deleted is a leaf node, simply remove it. If not, swap the node to be deleted with the last leaf node in the heap. After swapping, remove the node you wanted to delete. Lastly, perform heapify on the array to rearrange the elements correctly. Remember, for a min heap, we modify the algorithm so that both child nodes are smaller than the current node, ensuring the appropriate structure of the heap. Now, let's talk about the peek operation, which allows us to take a look at the topmost element of a priority queue without actually remove that element. So this is helpful when you want to know the maximum or minimum value without altering the order of the queue. So here is how the peek operation works. When you perform a peek operation on a max heap, it will return the maximum element presented in the heap. Similarly, when you perform a peek operation on a min heap, it will give you the minimum element. The process is simple. By returning the root node, which is the highest or lowest priority element depending on the type of the heap, you get a quick way to access the significant value without any changes to the heap's structure. Now, let's explore the extract max and extract min operations in a priority queue, specifically in the context of max heaps and min heaps. When you perform the extract max operation on a max heap, it retrieves the node with the maximum value of the heap and removes it. Similarly, extract min operation on a min heap does the same but for the minimum value. Here is the simple way to understand it. With extract max, you take out the highest priority element, the one with the largest value from a max heap. With extract min, you do the same but for the min heap, extracting the lowest priority element, the one with the smallest value. In both cases, the extracted element is removed from the heap and the structure of the heap is adjusted accordingly to maintain its properties. Let's take a look at some practical ways priority queues are used in various applications. Dijkstra's algorithm. Priority queues are a key component in Dijkstra's algorithm, a method used in finding the shortest path between nodes in a graph. The algorithm relies on the concept of choosing the next node with the lowest distance value, which aligns with the priority queue's functionality. Implementing stack. Believe it or not, priority queues can be used to build stacks as well. By assigning priority values to elements and extracting them accordingly to their priorities, you can effectively create a stack-like behavior where the most important element is accessed first. Load balancing and interrupt handling. In operating systems, priority queues help manage tasks efficiently. For instance, in load balancing, processors are assigned priorities to distribute the computing load evenly. Similarly, for interrupt handling, when hardware signals need prompt attention, priority queues ensure that the most critical tasks are addressed first. Data compression using Huffman code. Priority queues are essential in creating Huffman codes, a technique for data compression. In Huffman coding, characters are assigned varying length codes based on their frequency of occurrence. Priority queues come into play during the process of constructing this code tree. By understanding these applications, we can see how priority queues play a crucial role in optimizing various computational tasks and improving the overall efficiency of systems.